Here is the very first example. This is a past year from MJ16 P52. So I'll just write that down in the corner. And this is a throwback to a once upon a time, MJ16. Once upon a time paper 3 question, because this has appeared before. Anyway, what we have here is you are trying to investigate the acceleration of a trolley moving up an inclined plane. Oh, this is going up, yeah. That's a little bit different from what we're usually doing, roll it down the slope. So here they give you a diagram. Oh, bless. If they give you a diagram, means you can probably build on that exact same diagram. But what we're investigating here, we're investigating the relationship between acceleration, so I would probably underline that, and the angle of the inclined plane. Now, which one do you think is the independent variable and dependent variable? You should start thinking about that already. When a force F is applied to the trolley, okay, it's suggested that the relationship is this equation, where G is free fall, M is mass, K is a constant. Wow, okay. Take note. Design experiment to test the relationship between A and theta. So these two are the variables that we are trying to test. One of them is IV, one of them is the DV, independent and dependent variables. Then we need to explain how the results can determine a value for K. Oh, so this is ultimately the goal of this experiment. Relationship between A and theta, determine the value of K. So at the end, I must remember to write an expression for K. Okay, so I think that's it. They tell us what we should pay attention to, blah, 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 procedure, everything. Okay, so before I start, I think I want to plan my experiment a little bit, gather my thoughts from what I just read. So what I could do is, bam, I start off with a table. So this is a table that I talked about in the intro video. How, I mean, you don't have to draw this exact thing during exam, but it's nice to know what you're supposed to do. So based on what I've read, it sounds like our independent variable, what we change, would be the angle theta of the inclined plane. How steep is it? And in response, we are trying to measure the acceleration. So A and theta, so acceleration will be another one. Okay, so let's write there acceleration. A. What is unchanged? Let's go back to the question. Now they give you a bunch of constants here. F is constant. M and G is constant. K is constant. But experimentally, what you can choose though is to make F constant force, and of course the mass of the trolley M. Oh, all right, let's start with that. So there can be two possible constants, F, the force pulling the trolley up the slope, or the mass of the trolley. So that's the first thing to start off. And then maybe I should think of how am I gonna set up the angle? Well, I probably need a protractor and some kind of jack to, lift the inclined plane up. Otherwise, how is it gonna stay up there? So the jacks are the ones where you can kind of do something like that to change the angle. Okay. How about acceleration? Usually we will need a distance and time, light gates maybe. So here, if you're measuring acceleration and you're pushing something up the slope, it's usually easier to use light gates instead of a stopwatch and distances. So light gates. We'll go into more detail on what light gates are in case you have not seen them or used them before. Constant. How to measure the F and M? Oh, force can use Newton meter to measure because we want to keep it constant. Mass, I guess we could use a digital balance. You know the ones in lab where you put it there, you press a button, and then the reading shows? Yeah, that's a start. So here I'm still planning. I'm not writing the answer yet. Extra details. Can I think of any ones now? So for angles, protractor, I should probably secure it with blue tack. Anything I need to say? Calibrate repeatedly. Yes, I will have to repeat. This one. Take repeated measure values of A. Probably a few times. What else do I need to do here? I need stopwatch. Oh, I need stopwatch. Do I need a stopwatch? No, I have light gates. Oh, I will need a card for trolley because I'll be using light gates. Okay. What else for the force and M? Any other extra details I can think of at the moment? I should probably use a string to pull the Newton meter because, force What else? Mass of trolley. Use same trolley lah. I guess use same trolley. So this is my thought processes as I am doing my first round of details. I'm trying to think as much as I can, but don't get stuck here too long. This is just the planning part. Now, with this in head, I was like, okay, time to move forward. Oh wait, acceleration. Yes. How are we gonna measure acceleration? See the slope here, right? If I can measure the initial velocity and final velocity with light gates, I know the acceleration. So light gates are something like a beam of light. Let's say this a green laser light. This trolley with a card will pass there, and the light will scan. So it will know if you have a distance of the card, which is, I don't know, call it X. The light gate will measure how long it takes for that card to pass by, and from there it can measure the initial velocity. Okay, so I probably need a card too. I already mentioned that. Okay, so let's get started. Now that I have a rough idea of what I'm measuring, what are my variables, I can start. So I'm going to try to go side by side along with the template so you can see how I can use that. So let's follow the template. First start. Diagram. Use ruler, draw a clear diagram. Label all apparatus. Okay, let's do that. So the nice thing is they already gave a diagram. Woohoo! So I can draw pretty much the same thing. Now, it says to use a ruler, but you know, digitally it's a bit hard to draw with rulers. So I will try my best to draw something that is not weird. There, 2 lines. Okay, that's a start. Next, we need something to elevate this plane. We can't just leave it hanging there, right? So this is the angle that we want. Just a table. I guess I could label that as well. Oh, why not? Something to elevate. Maybe I could use a jack. A jack looks something like this. Usually has something there and has a screw somewhere. I should draw something like that. Maybe you've seen this before in lab. Okay, so it's like this. You got a wire, something here. There doesn't need to be an artist lah. Roughly, you didn't do this is okay. So just label this as a jack to elevate the slope. So the slope will be this thing. Slope. So I should label that too. Now for our trolley. The trolley is going to be pulled up. So I guess I could draw somewhere here. Oh my. Draw trolley. The wheels. And it's attached to the Newton meter. So I draw a Newton meter. I have to label all this later. Newton meter also tied to a string lah. Okay, so tied to a string. Again, I repeat, use a ruler if you can. Yes, on paper with a ruler. Anyway, Newton meter is this friend right here. Newton meter. And this is our good old trolley. What else should we label? Oh yes, card. We need a card and light gates to measure acceleration. So I'm going to put a card on the trolley. Say, hey, there's a card with a certain length X here. Or I should say certain length L. Okay lah, L lah, L. Let's use L. L for length. And what other things I should label? Light gates, right? That's the main performer of the party. So I'm going to put a light gate right up here. You know, light gates are usually U-shaped one, right? Usually lah, but different variations. As long as I put one up here and one somewhere at the bottom, I should be fine. Okay, what else should I label? Maybe I should also label distance S between the top and the bottom. For good measure, why not? Okay. Now, what else do we need to do? Light gate connected to computer. I should label that. So light gate to computer. That's how you read it, right? To computer. It's another light gate. Okay, something like that. Pretty, looks okay. If I miss something out, I'll just come back and draw it later. So don't worry about it too much. It's a good start. Okay. Oh, protractor. Ah, man, where should we draw the protractor? We want to measure the angle, so I should draw a protractor here. There we go. To measure angle. Okay, I'm just going to leave it as that protractor. I think I'm pretty satisfied for now. If I miss out something, I'll just come back later. But this is my diagram, part A. Okay, I think we are done with A. Use a ruler, clear diagram, label everything, including table. Sure. Alright, next, I need to define the problem. So I need to state what is my independent, dependent, and constant variable right in the answer itself. So that will be, oh, down here, look, there's lines. Now this is the actual exam paper, so this is how it looked like. So B, I am going to define the problem. So I just label lah, add a heading to make it easier for the examiner to mark. So the first thing is independent variable. I need to say what that is, which is, what am I changing? Angle of inclined plane, which is theta. What is the dependent variable? If you think back to earlier, we say the thing that will change in response to me changing the theta, and that will be the acceleration of the trolley. Then we also have a constant variable, or a few constant variable actually. One of it we want to set as a constant is the force on the trolley. And this is the one that is caused by the Newton meter pulling it. Okay, so that's one. The other one I want to keep constant is probably the mass of the trolley as well. Okay, I think that's good. That's a good start. Constant variable, force of trolley, mass of trolley. Okay, that's done. All right. Next. So this is done. You may say, Miss, shouldn't gravitational acceleration also be constant? Yeah, but you can't really change it in the first place unless you go change planet. So now we don't have to mention G. F and M is good enough for constants. Okay, the next section is the methods of data collection, also known as the method section. So let's just write this sentence. Set up the apparatus as shown in the diagram above. Okay, let's go. So C is the method section. So put a nice big header and start with point number 1. There, I wrote it out. What else do we need to talk about? Okay, so you just think through all the variables now. There's the independent variable, constant variable, and independent variable by all this stuff. So how are we going to vary the independent variable? Details to vary. Preliminary readings to ensure a workable range of values. Any safety considerations? Not too much. Wait, safety. This reminds me. You know, if the trolley suddenly detach and roll down, wouldn't that make a big noise or some kind of thing? So maybe I should add a sponge here. Sponge. You know, those things where they're like yellow color sponge, where the trolley hits it, at least the trolley doesn't roll off the table and like drop down, maybe injure somebody. So maybe that's a safety consideration. I don't know. I would include that as well. So we need to talk about independent variable and constant variable, instruments, and other things. Okay, so let's start here. Let's start off with the constant variable, because usually that's the first one I would start off with. So what's the variable? F and M. So I'm going to measure the mass of the trolley itself. So I will use a digital balance to measure the mass of the trolley. Then I also need to make sure my force is a certain fixed value, right? So see, I'm gonna pull the string, and so the trolley is gonna go up the slope that way. So I should probably, I'll just put a label here, F. That's better. So I need to do a trial run. So I'll pull the trolley at a steady speed and measure F. I'll record F. Now I should correct that. I said pull a steady speed. No. It should be pull a steady force and record that F, which should be a constant value. So you try to keep it constant lah. You see the F, try to make sure it's constant as you pull it up. So I know this is very tricky to do, but we do what we gotta do. There's another method to use, pulleys, which is totally possible as well. For those of you who are wondering, what am I talking about? If you have an inclined plane, you can put a pulley here, hang some masses, and do it like that. Sure, that works too. But there's too many ways you can do this experiment. I'm just going to do this one way, okay? So we're done with the constants. Now we talk about our other variables. We are changing the independent variable, which is theta. So we need to talk about theta. So we can say raise the jack. Oh man, this should go before here. Never mind. Order is out of the place. Anyway, raise the jack. Assume the jack is already raised. So I'm going to change that. So we need to measure angle theta. So measure inclination angle with what? Protractor. So we can say that. Okay, I think that's our IV done. So IV Oh, how to vary. Oh, we should include this later. So this one's not done yet. So range of variable range. Okay, already did pulling it up. Safety consideration. We already put the stuff. We already measured the mass. So this is mass and force. We're going to use Newton meter and digital balance. Okay, what else? Okay, so measure the independent variable by, we said we place a protractor. This is done. Safety considerations, nah, not too much danger changing data. Any limitations or suggestions? Data, now should be okay. There may be some, you might argue there may be parallax error, but no, usually we don't talk about parallax error. We assume you have a good eye and good scientific method. So now let's go on to the dependent variable. We'll leave this one up here for a bit. Dependent variable, what is changing? Acceleration. Oh, this is going to be the one that's a little bit tricky. So how are we going to measure acceleration? We need to include details about that. And how to measure, oh, light gate, we already mentioned. So let's go to see how we can do acceleration. Okay, let's go to the steps. So I'm going to say this way. You can start the light gate timer. You know, you just tell the light gate like, hey, get ready or stand by. There are many different light gates, but you're going to start the light gate timer and pull the trolley up with a constant force, with the same constant force as you did before. Try to keep it constant lah. There's perhaps something to mention here as well. You know, when we pull the trolley up, right, this thing should probably be parallel to the slope. Otherwise, if you pull at the angle, then your force isn't exactly what you want already. So yeah, we should figure out a way to put that there. So maybe you include a spirit level. So I probably put in bracket here. Use spirit level to make sure that the string is parallel to the slope. Or any other method lah, you think of it. However you want to describe that. Okay, this one is pretty flexible. This experiment, this question, you can be as creative as long as you hit the points. Okay, next. So we pull it up, the light gates measure stuff. How are we going to measure acceleration from this? Man, what does the light gate actually measure? It measures time. That's it. That's all the light gate can do. Start timer, stop timer, start timer, stop timer. So we need to do some calculation now. Remember just now I said measure card L, right? This L here. Why did we have to do that? That is to enable us to calculate the initial and final velocity. So I'm going to do that next. Alright. Now, I'm not sure this one may not get a point, but I'm just going to write it down just in case there's some detail in it. So I'm going to calculate the initial velocity with the length of the card over the time of that first light gate. So the first light gate will be the one down there. Number 1 is down here on the right side. Number 2 is the one up there on the top. So the card will pass through the light gate at a certain time. So that is going to be a T1. And how about T2? Final velocity. And V2 equals to the same length of card, but now a different time. So I have my final initial velocity. And from there, I can find my acceleration. But I need to include one more thing, which I forgot to include earlier. This will happen in exam. You're like right halfway, you're like, oh, forgot to do that. So maybe it's good to leave some blanks lah, especially in between sections. So I'm gonna write that here. Record distance between light gate. That means that will be the distance that the trolley traveled. So I'm gonna name this S. If you look back at the diagram that I drew, I have already labeled S, but I forgot to mention it. So here, between the light gates, it travels a certain distance. Okay. So now we can calculate acceleration. So we're gonna do that. Calculate acceleration with, we know initial speed, we know final speed, we know the distance. If I may remind you, there's this thing from AS, v squared equals u squared plus 2as. The forces are constant, so the acceleration is constant. So I can rearrange this thing to become what is this? V square minus U square equals to 2AS. So I say acceleration equals to V square minus U square over 2S. So this is one way to calculate acceleration. There are different ways with timer. There's many acceleration formula, but this is one way I'm going to do this. So, okay, I know how far the trolley traveled. I know the start and stop speed. I can find the acceleration. I think we are good here. So let's go check. Go back to the checklist. How are we going to measure that? Okay. Any safety considerations? No, we already mentioned the sponge. Limitations, suggestion? Take average. So we need to think about this one. That's step number 6. So trolley is a bit jittery. There's a lot of uncertainty there. Maybe your hand move a bit. The force is different. So it's good to obtain an average. So let's mention that too. So average. Why we average? To reduce random error. Okay, let's keep going. I'm trying to write as much detail as I can, so you may not write such detail. That's okay. It's your first one. Let's give you an example. Okay, so how are we going to write this thing? Same angle, you need to repeat the experiment a few times. Take average. Like what we do in AS, repeat, take average. So we can say, for the same angle, we repeat experiment. So experiment is repeated to take many values of A. So that is this part. Find average, repeat, take average. This one you can for your dependent variable. Okay, because it's going to be hard to measure. So good to give instructions as well. So that will be this thing, averaging method. I think we're good for now. What else are we missing? How to vary independent. Oh yes, we should include that. How to vary independent variable. That's where we come here to repeat. So you're going to repeat certain steps, and you need to think about how to change the angle now. So let's go to that part. Now this is where you may realize if I want to say repeat steps 1 to 3, I didn't label the steps there. So that is good too. Label the steps instead of put bullet point. Okay, let's change that. So now that we have labeled in numbers, it's much easier to say which one you should repeat if you want more readings. So it looks like we can repeat steps 4 until 7. These are the ones that we will repeat for different angles. So no more space now. So I write next line lah. Okay. So number 9, what are we going to do? Increase or decrease the jack height. I guess it's easier to decrease. Let's do that. So decrease the jack height. So make the thing less steep. And repeat steps. What steps are you repeating? 4 to 7, right? Okay, so repeat steps 4 to 7. Oh, and also to vary. I should say 4 different values of theta. We are changing angle of theta. Data is recorded in a table. Should I draw that now? Yes, I can draw that, but I don't need to say that out. So I'm going to try draw a table to illustrate what am I changing. So usually the first one is theta lah. We are changing theta. Do I need to write units? Nah, I don't need to write units for now lah. Okay. So I'm changing theta. I'm measuring. What am I measuring? For my dv. dv is the velocity measured by the light gates. Okay, so that one is pretty straightforward. They will measure for me. Should I write both? Okay lah, T1, T2, V1, V2. Ayo. Never mind lah, I just put V1, V2. So anyway, V1, V2 will be able to give me the acceleration A. And I need to take a few average lah. So I will assume that this one, they are taking average. So I won't draw everything unless the table becomes very, very long. What else do we need to know? Well, the other things that we recorded were the length of the cart. So maybe I list that down. Mass of the trolley. Okay, what else did we record? Distance of the slope. I think that's it. Okay, so we can list this here as our things. And then, of course, you will take many reading, so your table will become very long. And that is pretty much the end of the method section. Yeah, I included a lot of details already, so hopefully this is enough, more than enough example of details for you. Now let's go on to the final part, which is the analysis section, which is much shorter in my opinion. So we need to go back to what, okay, we got this table of values. What are we going to do with it? So we go back to our equation that was given to us once upon a time. I have written it down here so I don't have to scroll all the way up. But this is section D, analysis. So let's label section D, analysis. So my equation was, what was it? MA equals to F minus mg sine theta. And I'm going to open up the bracket, so this will be minus K. How on earth are you supposed to create a straight line with this? Don't panic. Remember, we are trying to find the relationship between A and theta, which is stuck to the sine, so that you put the whole thing together lah. So this can become a straight line equation, and you can linearize it. Now, there are a few ways of doing this, but up to you. If you look at the mark scheme, you will find that there is a few ways of doing this. So I'm going to rearrange this first into something I can recognize. So this will be negative mg sine theta. Everything else is constant, right? I throw at the back, plus f minus k. It's all constants. And I want to keep my dependent variable by itself, so I'm going to divide everything by m. So this will be negative g sine theta plus this whole chunk of constants, f minus k over m. Oh, very nice. Do you recognize this? Y equals to negative m x plus c. So there are parallels here. This is my x, this is my y. So what am I going to plot? Draw a graph for you that you can see. So this one, if I plot a graph of A, my dependent variable up there, against my x, which is sine theta, what will be my gradient and my intercept? That's important to know. So based on this thing, it should roughly be like that, because a negative gradient ma. So the gradient here will be negative m, which is this one. Sorry, negative, and negative g. G will be the gradient. Intercept. Oh yes, intercept. Intercept here will be this one, which is f minus k over m. So you plot your points, draw a straight line, you will get a graph like this. Okay, let's go back to the sheet to check. What else do we have to do here? Oh, in the given equation, what is constant? Okay, you identify. This one, if you can identify, sure, identify. If you have not earlier, show your steps to linearize the equation. Okay, you do already. Plot a graph of this against this. Oh, we draw a graph, but we didn't say this. Sure, okay lah. Just in case lah, I say lah. So I'll write it in a sentence. Plot a graph of A against sine theta. Must be sine theta, cannot just theta, because theta it's not gonna work. Now the final step is to identify lah. What is gradient, what is y-intercept? If the relationship is true, how can you proceed? So we need to show what is gradient, what is intercept, and what is the constant to find. Three expressions that we must write. So let's write it down. Let's go. So based on this, all the colorful thing I did up there, you can say something like this. The gradient, one sentence lah. I write here. Gradient is, although we don't need the gradient, we can just write it out, negative g. Y-intercept, which is the most important one, equals to f minus k over m. So we are trying to find what again? Remember, way in the beginning, we scroll all the way back. What was the problem we're trying to find? The red color one. These. We are trying to determine the value of k. That's the purpose of this whole experiment, right? So you need to think of, okay, if you have a graph, how are you going to find k? Let's rearrange. So let's just write it down. Rearrange from y-intercept. Hence, let's see, y-intercept times m. Okay, so y-intercept times m equals to f minus k. So I do one more step. K will be f minus y-intercept times m. There. So this is the important ending that you must reach. You want to find k, right? This is how you find it, based on your graph, which is whatever value you get for your y-intercept. Everything else we can plug in, we measure already. So one last statement to wrap this up is to give, how do you know if this thing is valid or not? So you need to do what? You need to talk whether a relationship is true or not, Okay. So one way to talk about this one is, how do you know whether your data will fit this thing, this graph that we just draw here? It's a straight line graph, so okay, you mentioned something like that. So it's a straight line graph and it must have a y-intercept, otherwise you cannot find your k. So we can say something like this: the relationship is valid if, this is how you can generally start the question. The relationship is valid if, it's like saying, how do you know the graph is straight or not? Never mind, we just say if it's a straight line, so graph is a straight, out of space, straight line, and y-intercept is there, so it does not pass through the origin, and does not, because it has an intercept, pass through origin. Some of you may be wondering, Miss, do I need to talk about the gradient and all those things? No, not exactly lah. I mean, you can mention gradient should be negative, decreasing, intercept should be f minus k over m, but no need. You already mentioned that up here, so no need lah. You just want to know whether it's straight line or not. Is the equation correct or not? Okay, so I think that is the end. Now the last part is additional details. At this point, if you still have time during exam, then you think you sit there, you stare your experiment. Did I forget anything? You forget, faster go and add at the end. Okay, so I would suggest, if you did not already include it earlier, safety suggestions, safety consideration, will anything harm you? Trolley will drop down or not, hit your face? And any suggestion to improve accuracy, like take average, that is considered additional detail already, but I already included earlier. So any other thing you miss okay? If here you already mentioned whatever is here, see, safety consideration. If you already mentioned here, no need already lah. So if you have anything, please include it here. Extra details. Extra details. If nothing, no need to write. Nothing. Done. So that is the whole journey of question 1. Wow, this takes time. As you can see, even the video length itself is already about 30 minutes, and you have suggested 45 minutes to do this thing from start to finish. I know I pause a bit in between so I can write, but yeah, it's good practice to train yourself to do this. The first time, right, you won't be able to think of so many details, so I will highly recommend you check out the next video, which is about marking this paper and how to understand the mark scheme when you are doing this. Okay, the mark scheme will really train you to help think about the whole experiment and extra additional details that might be helpful. Okay, because the additional details are the ones that are hard to get marks. Also, my final advice for you for this question, this kind of question, is think back to when you were in lab for AS, doing lab. Maybe you need to imagine a little bit the scenario, like, how do I think of this thing? What was it that was very hard to do? The thing may be shaking. Oh, Miss need to add blue tag so that the slope doesn't shake. Yes, you think of that, you mentioned that. All these are good details that you should add. Okay, so that's all for this demo on how you can do question 1. Lots and lots of details all in one. Full force for you. Okay, so go try out some of these by yourself, and all the best in your question 1. Go check out, and I'll see you in the marking video.